Hi everyone, thanks for coming to my presentation. I am Jianpei from the City College of New York, and today I'm going to be presenting how does a evaporation-driven linear actuator work and its potential application. First of all, I would like to talk a little bit about evaporation of water. As we might know, evaporation of water involves phase change from liquid water to water vapor under certain chemical potential gradient. Figure on the left shows the relation between the Earth's water cycle and solar energy. Evaporation on Earth consumes about 50% of the solar energy it receives in a yearly basis. And the amount of energy is so large that it drives the water cycle of Earth. In other words, evaporation happens almost anytime, anywhere. Despite this huge amount of energy circulating around us, we are not very good at using it so far. But unlike us, nature has been using it for a very long time. Like this video shown right here, PyCon open and release seeds when it is dry, and it closes up when it is wet. So here's the question: what can we learn from that? So PyCon composed mainly of cellulose, which is a type of water-responsive material. A water-responsive material is a material that changes shape when the relative humidity changes, and baking paper does it too. It expands when it is wet and contracts when it is dry, as shown in this video. And the plot next to it. The number of identical cycles shows that the process is highly repeatable. So paper is actually very good for demonstrations of devices use evaporation energy. One way of using it is to pack as many identical paper strips as needed to make an artificial muscle like this. And the next thing you need to do is to build a control volume like this box. As you can see, the air comes in from both sides of the box and leave at the top. And the period structure right here is used to output work. More details are shown on this export view, with the only moving part being the muzzle front. The whole muzzle is placed on the middle tray with a lot of little holes on it, and the purpose for this is to get a uniform chemical potential gradient. Now let's take a look at how we deliver air. Air comes in from the pressure regulator, and then we use solenoid valve 1 to deliver dry air and solenoid valve 2 to deliver humid air. The humid air is generated by passing a dry air through a water source. And to provide control, we use a microcontroller called Arduino. The Arduino is a programmable board that can receive or output digital or analog signal. It can be programmed by Arduino IDE, MATLAB, or Python. In this case, we only use digital pin 3 and 4 to generate digital signal as shown in this figure. Let's go back to the circuit diagram. The signal comes out from the microcontroller and it is amplified by the two MOSFET right here to open or close the switch 1 and 2. There are 4 LED to be used to indicate if the circuit is functioning properly, and there are 4 resistors is used to provide protection for the LEDs. Resistor R5 and R6 is used to protect the two MOSFETs. And the picture right here shows how the actual circuit looks like. In the computer science, uh, what happened is we need to set up a process time, and then we need to input the time delay for each valve. And finally, we can loop the process for as long as needed, uh, as shown in this pseudocode. This video shows a test of the linear actuator lifting a 1 kilogram load for a couple of cycles. And the schematic diagram on the right shows how the deformation of the muscles is converted to the elevation of the load. The table on the right shows the force output of the actuator is about 147 Newton and a work density of about 71.6 kJ per cubic meter. Despite the force output is large, the problem is the process takes too long to complete. One major reason might be the insufficient airflow, which make poor contact on the surface of the muscles. So we plan to use SolidWorks simulation to analyze how different design lead to different flow simulation. Two example plots are shown below. One is the flow trajectory plot with density gradient and a surface plot with pressure gradient. We will do more analysis to improve the performance in the near future. So in conclusion, the linear actuator is easy to program and it can be integrated into different systems, like a radial engine. We propose an evaporation-driven radial engine with the linear actuator being the pistons. We also use Python to simulate the position of one of the pistons, which respond to the valve state, and we hope to build this special engine in the near future. Finally, I want to thank Dr. Chen and Zilun for the greatest technical support to me, and thanks everyone for listening.